AdaBoost uses this slightly intimidating formula to figure out what W hat t should be. But it turns out to be pretty intuitive if you look at it in a bit more detail. This formula is derived from a famous theorem, AdaBoost theorem, which we're going to mention very briefly towards the end of the module. But it's the formula that lets you find classifiers that keep getting better and better and helps boosting get to the optimal solution. So let's look at this formula in a little bit more detail by exploring a few possible cases. So the question is ft good? If ft is really good, it has really low error on the training data, let's say weighted error. So for example, if that weighted error is 0.01, then it's a really good classifier. The question is, first, let's see what happens to this famous middle term here when the weighted error is 0.01. So the middle term is 1 minus 0.01 divided by 0.01, which is equal to 99. And next, to compute W hat t, we're going to take a half times the log of this number 99. And so if you do 1/2 times the log of 99, you're going to get 2.3. So this was an excellent classifier, and we gave a weight of 2.3, which is high. Now, let's see what happens if we output a random classifier. So as we said, a random classifier has weighted error of 0.5. It's not something to be trusted. So if you plug this in, 1 minus 0.5 divided by 0.5 yields the magic number 1. And if you look at half of log of 1, what's log of 1? It's 0. So W hat t is 0. So what have we learned? If a classifier is just random, it's not doing anything meaningful, we count it by 0. We say, you're terrible. We're going to ignore you. And you might have friends who are kind of like this. They say random stuff. You never trust what they say. You put 0 weight on their opinions. So that's what AdaBoost does too. Now we're going to get to a really, really, really interesting case. Let's suppose that your classifier is terrible. It gets 0.99 weighted error. So it's getting almost everything wrong. It's worse than random. Let's see what happens to the term in the middle here of our equation. You get 1 minus 0.99 divided by 0.99, which is equal to 0.01. And guess what happens when you take a half log of 0.01? You get minus 2.3. And when I first saw this, I thought, wow, this AdaBoost theorem is beautiful. But take a moment to kind of internalize what just happened. We had this terrible classifier, but yet we gave it pretty high weight, 2.3, but with a negative sign. And why is that? Because a terrible, terrible classifier might be terrible, but if we take 1 minus f of t, so if we do exactly the opposite of what it says, it's an awesome classifier. In other words, if we invert the sign of the classifier, we're going to do awesomely. And AdaBoost automatically does that for you. And so this is, again, kind of using the friend analogy. You might have a friend who has really good opinions, but they're always like wrong. And so you do exactly the opposite of what that person says. Maybe this is how you hear your parents or something, or some friends. You say, okay, you say I should do A, I'm going to do the opposite of that. And by doing that, I might do great things in the world. And so AdaBoost automatically figures that out for you, which is awesome. Now let's revisit the AdaBoost algorithm that we've been talking about. And in this part of the module, we've been exploring how do we compute the coefficients W hat t. And we saw they can be computed by this really simple formula. We compute the weighted error of f of t, and we just say that the W hat t is 1/2 of the log of 1 minus the weighted error divided by the weighted error. And with that, we have our W hat t's, and we can focus on figuring out how to come up with alpha i's. And we want alpha i's to be high where ft makes mistakes or does badly.